Arthur Hartley stood on the deck of a converted coaster somewhere off the Kent coast, watching 3 inches of rubber, lead, and steel wire disappear into the grey water behind him. And he knew that almost every senior officer who had heard his plan thought it was a fantasy. Pump petrol across the English Channel, under the nose of the Kriegsmarine, through a pipe laid on the seabed like a length of undersea telephone cable. No one had ever tried to move fuel that way, at that distance, under fire. Engineers at the Admiralty had called the idea impractical. Some had simply laughed. And yet here it was, spooling off a giant drum into the sea, with an invasion force ashore in Normandy already burning through fuel faster than any tanker convoy could safely replace it. The stakes behind that moment had been building for 2 years. By the summer of 1944, the Allies had put more than 1 million men ashore in France, along with the tanks, lorries and aircraft needed to break the German army in the West. Every one of those machines ran on fuel, and fuel was the single most vulnerable link in the entire invasion chain. Tankers crossing the Channel could be sunk by mines, torpedoed by E-boats, or caught by the Luftwaffe. A single successful attack on the fuel convoy could stall an armoured advance for days. The planners of Operation Overlord knew that whoever controlled the flow of petrol controlled the pace of the war in Western Europe, and they knew that ordinary shipping alone would never be fast enough, or safe enough, to keep pace with Patton's tanks and Montgomery's divisions once they broke out of the beachhead. The man tasked with solving that problem was not a naval architect or a soldier. Arthur Hartley was the chief engineer of the Anglo-Iranian Oil Company, a civilian used to building pipelines across deserts, not war zones. In 1942, after the disastrous Dieppe raid exposed just how difficult it was to capture a working port intact, Hartley proposed something that had never been attempted at any scale in military history: laying flexible pipelines along the seabed to pump fuel directly from England to the continent, bypassing ports and tankers altogether. His inspiration came from an unlikely source. Submarine telegraph and telephone cables had been laid across oceans for decades, coiled onto huge drums and paid out from ships as they steamed forward. Hartley believed the same principle, scaled up and adapted, could carry not electrical signals but aviation spirit and diesel, mile after mile, along the floor of the Channel. The idea reached the desk of the Petroleum Warfare Department, a wartime body under the government minister Geoffrey Lloyd, created specifically to solve Britain's fuel supply problems for the invasion of Europe. Lloyd backed Hartley's scheme, and it soon found a powerful ally in combined operations, then under Lord Louis Mountbatten, whose staff had already learned from Dieppe that ports would be fiercely defended and possibly wrecked beyond use even if captured. But backing from a minister and an admiral did not silence the skeptics. Naval engineers pointed out that no cable, however strong, had ever been asked to carry high-pressure petrol rather than electrical signal across open water, in conditions that could include storms, strong tidal currents, and enemy attack. Some questioned whether a pipe could survive being dragged across a rocky seabed at all. Others thought the entire scheme, soon given the deliberately unglamorous codename PLUTO, Pipeline Under the Ocean, was an engineering fantasy dressed up as a military plan. Hartley pressed ahead anyway, working with cable manufacturers who had spent decades solving exactly the kind of problems the skeptics were raising, even if not for this purpose. 2 rival designs emerged, developed almost in parallel, each betting on a different solution to the same problem. The first, developed by Hartley himself, along with the Siemens Brothers Cable Company, and the engineer B.J. Ellis, became known as HAIS, an acronym built from the names of Hartley, Anglo-Iranian, and Siemens. It was a genuinely flexible pipe, built layer upon layer like a submarine telegraph cable, a lead-lined core to carry the fuel, wrapped in paper and cotton insulation, armoured with steel wire and reinforced further still, all of it flexible enough to be coiled onto a drum and paid out from a moving ship, exactly as cable engineers had done for generations. The second design, developed by the engineers H.A. Hammack and Ellis and known as Hamel, took a different approach. Rigid lengths of ordinary steel pipe, welded together in sections, and wound on to colossal floating drums so they could still be paid out at sea like a cable, even though the pipe itself had none of the natural flexibility of Hartley's design. Both approaches faced the same brutal question. Would they actually work once they were unspooled onto a hostile seabed and put under pressure? Before anyone dared answer that question in the middle of a war zone, the teams needed proof, and they needed it in conditions that mimicked the real crossing as closely as possible without giving away the plan to German intelligence. The first trial in the summer of 1942 was modest, almost to the point of secrecy. A length of experimental pipe laid across the River Medway in Kent, testing whether the basic principle of paying out a fuel pipe from a drum and pumping liquid through it under real conditions could work at all. It did. That success bought the program just enough credibility to attempt something far more ambitious. Later that year, engineers staged a full-scale trial across the Bristol Channel, running a test line roughly 30 miles from Swansea in South Wales to Watermouth, near Ilfracombe on the North Devon coast. A stretch of water chosen deliberately because its currents, depth and distance came close to matching the conditions the pipeline would face when it eventually crossed to France. It was here that engineers first proved they could lay a working fuel line across open water at meaningful distance and actually pump petrol through it from one coast to the other. For the men on the barges and the tugs involved, this was the moment doubt began to give way to guarded confidence. But a successful trial in home waters, with no one shooting at you and no invasion timetable hanging over your head, was one thing. Doing the same thing across the most heavily defended stretch of water in occupied Europe was another matter entirely, and everyone involved knew it. To lay the cable at the scale needed for a genuine cross-channel supply line, engineers designed something almost as strange as the pipeline itself. Enormous floating drums, 70 or more feet across and weighing over 1,000 tons once loaded, built to hold many miles of coiled pipe and float freely so they could be towed across open water by tugs, unreeling their cargo as they went. The drums were given the deliberately playful codename Conundrum, and to anyone watching from the shore they must have looked less like a weapon of war and more like a piece of industrial machinery that had somehow escaped from a factory and drifted out to sea. That, in a sense, was rather the point. Disguise and misdirection were as important to PLUTO as the engineering itself, because if German reconnaissance ever worked out what those drums were for, the entire fuel supply strategy for the liberation of Europe could be compromised before a single gallon crossed the Channel. By June 1944, with the Normandy landings underway, and Allied forces fighting to expand their foothold in France, the moment had come to test PLUTO for real. The first attempt targeted the shortest practical route planners believed they could rely on. From Shanklin on the Isle of Wight, codenamed Bambi, across to the port of Cherbourg on the Cotentin Peninsula, which Allied planners expected to capture and bring back into use fairly quickly after the landings. It did not go to plan. Cherbourg's capture took longer and proved far more destructive than hoped, with retreating German forces wrecking the harbour's facilities before Allied troops could secure it. Worse, when engineers did attempt to lay the HAIS line along that route, the pipe suffered real damage from the strong tidal currents and uneven, rocky seabed of the crossing, and early attempts to establish a reliable flow of fuel through it fell well short of what the advancing armies needed. For men who had spent 2 years defending this idea against skeptics who said it could never work, watching pressure readings fail to hold and fuel deliveries stall far below target, must have felt like exactly the vindication the doubters had been waiting for. It would have been easy at that point to declare the whole scheme a costly failure and fall back entirely on tankers and coastal shipping. Instead, the teams behind PLUTO adjusted their plan rather than abandoning it. As Allied forces pushed north and east through France that autumn, engineers identified a shorter, more sheltered crossing. From Dungeness on the Kent coast, codenamed Dumbo, to the French coast near Boulogne, and later Calais, once those ports had been cleared of German forces. The distance was far shorter than the original Isle of Wight to Cherbourg route, the currents less punishing, and by this stage the teams laying the pipe had learned hard lessons from the earlier failure about handling the cable, protecting it from damage on the seabed, and maintaining the pressure needed to keep fuel moving steadily, rather than in fits and starts. This time it worked. From the autumn of 1944 onward, HAIS and HAMEL lines were laid in growing numbers across the Dover Strait, each new pipeline adding to the total volume of fuel that could reach Allied forces on the continent, without a single tanker having to run the gauntlet of the Channel. Engineers and naval crews worked in difficult, often miserable conditions, laying and maintaining pipe in open water that could turn rough with little warning, all the while aware that a single serious storm, a single successful German attack on the terminal facilities at either end, could undo months of work in hours. By early 1945, multiple lines were operating simultaneously, and the network was delivering more than 1 million gallons of fuel a day to Allied forces pushing deeper into France, Belgium, and eventually Germany itself. Over the course of the campaign, the pipelines carried more than 170 million gallons of fuel across the Channel and later on toward the front. Fuel that no longer had to survive a sea crossing exposed to mines, torpedoes, and bombers. The significance of that achievement went well beyond the raw figures. Every gallon that reached Patton's tanks, or the fuel dump supporting the advance into the Rhineland through PLUTO, was a gallon that had not risked a tanker crew's lives on an exposed channel crossing, and had not required a warship or an aircraft to be diverted from other duties to escort it. As the front line moved further from the coast, engineers extended the system inland as well, running additional pipelines from the coastal terminals toward forward supply areas so that fuel could flow almost the entire distance from an English refinery to a forward airfield or armoured division, without ever touching a lorry convoy vulnerable to ambush or air attack. For an army whose armoured spearheads depended on a level of mobility that earlier wars had never demanded, that reliable, almost invisible flow of fuel beneath the waves and across the liberated French countryside became one of the quieter, less celebrated reasons the advance into Germany could be sustained at the pace it was. None of this had been guaranteed, and none of it had come easily. The engineers behind PLUTO had spent 2 years defending an idea that senior figures in the Navy considered close to absurd, had watched their first real attempt under combat conditions fall badly short of expectations off Cherbourg, and had been forced to rework their entire operational plan in the middle of an active military campaign, or without the luxury of admitting failure and starting again from scratch. What ultimately vindicated Arthur Hartley and the men who built HAIS and Hamel was not a single triumphant moment, but a stubborn willingness to adapt a genuinely novel piece of engineering under wartime pressure, using expertise borrowed from an entirely different industry, and to keep refining it until it did exactly what everyone had said it could not do. When the war in Europe ended in May 1945, the pipelines under the Channel and across northern France had already delivered a scale of fuel that would have been unimaginable to the officers who had dismissed Hartley's proposal back in 1942. Much of the equipment was later recovered, and some of the cable-laying expertise developed for PLUTO went on to influence post-war submarine cable and pipeline engineering. A quiet technical legacy from a project that had spent most of the war deliberately hidden behind an unassuming code name and a fleet of drums built to look like nothing more than floating industrial curiosities. Operation PLUTO never carried the same public recognition as the Mulberry harbours it worked alongside, or the airborne and amphibious operations it quietly supported from beneath the waves. But without it, the armoured breakout across France and the drive into Germany would have depended far more heavily on a fuel supply chain that German mines, aircraft and submarines could reach and disrupt at will. In the end, the men who insisted an undersea pipeline could carry fuel across a war zone were proven right, not through a single dramatic victory, but through the slow, unglamorous, and ultimately decisive triumph of an idea that almost no one in authority had believed in when it was first put on the table.